Hi Math 1 students. This video is to assist students who would like a little bit extra clarification on residual plots and what we've been doing with scatter plots. We took notes in section 9.5 in our last module. It's on page 32, and I'm just going to reference that very quickly. You can see that this starts off with this picture. There is a table, and this is an actual experiment. Guys, this is an experiment that we ran in Math 1 going back a number of weeks ago, where students were setting up bridges made of spaghetti. Depending on how many pieces of spaghetti, students would put in a given number of pennies to find the breaking point when the bridge would break, and they'd record their data. And this is actual data that was collected. You can see that we've got, for one piece of spaghetti right here, we're at 16 pennies. You can see I've highlighted in green right here when we had two pieces of spaghetti, it would have taken 40 pennies. Guys, what you'll be doing in many of your science classes is something very similar. You will collect data. You will record this data. X, we are told, should be the number of pieces of spaghetti. So look what happens right here as we begin to make a graph. We label number of pieces of spaghetti. Here would be our X values. Our Y would be number of pennies. The scale, paying attention to how large these numbers are, is very, very, very significant. You can see what is happening. We just plot these points like 2, 40. You can pay attention to the Y scale. It looks like we're going by 20s. I'm going to change this highlighter right here and really just make this green right here. There is 2, 40, and I guess what I really, really, really want you to understand is this is an actual data value. It's an actual point. It's an actual value. We've got the point 2, 40 right there. Okay, and you're going to see that there are plenty of actual points all around. Now, what you'll generally do in a science class or in so many other scenarios, you will plot your data and you will just have a collection of points. The big question is, could we come up with a line or perhaps another curve that you'd study in the future? But for right now, it's just a line. Could we find a line that obviously won't fit this data perfectly? That would be impossible. But could we find a line that gets super close and would best fit this data? What we're talking about is getting this equation is called a linear regression line. It's a linear regression line. It's also known as the line of best fit. And I've highlighted that in light blue. Of course, as we do that, you might find two friendly points and eventually, see that when I connect these points, I get awfully close to my data. We could come up with this line of best fit. We have an equation for that. That's a whole nother section that we reviewed to do that. We're not concerned with that presently in this lesson right here, but let's just say it's given to us. We have a linear regression line. How can it be used? Well, regression lines, lines of best fit, are used for predictions. You can see that our, data, we only went up to 10 pieces of spaghetti. You might say, what if we went out to 12? What if we went out to 11? You could plug in x equals 12, x equals 11, and you could get a prediction as to what we would expect for the number of pennies it would take to break such a bridge. So really, what you're seeing right here is a scatter plot. We've got our scatter plot. The scatter plot is just the plotting of those points. And then from the scatter plot, where we've got actual data points, actual values, we come up with a line of best fit. And here's where, guys, I really want us to remember what we did in 9.5. In 9.5, we had our first problem. It says use the linear regression, use that equation that we have, and you can see it's right here, y equals 21.88x minus 14.52. Use that to predict the number of pennies it would take to break a bridge made of 2 pieces of spaghetti. Remember, x is the number of pieces of spaghetti, so we could plug in x equals 2 into that equation. Now, I'm going to, just allow you to double check with the calculator if you'd like. 21.88 times 2 minus 14.52 is going to get you 29.24. 29.24. This right here is a prediction. We've got a prediction that when x is equal to 2, we'd have 29.24 pennies needed to break that bridge. That's really what it's saying. Now, of course, I highlighted in green, we actually have the true actual value. We knew it was 40. So the actual value is 40. So our prediction was not right. Our prediction was off. So I'm going to come back right in here and, really just make this jump out at you. We've got our blue line here, of course. There's a point on this blue line. That's the point 2, 29.24. That's what we'd predict. We are off, though. Really, the actual data point was 2, 40. So where is this leading? Well, it's coming over here to the side. We've dealt with the scatter plot. Now we're going to look at a residual plot. But first we have to talk about a residual. A residual is always going to be the actual y value. These are always for y values. Minus the predicted. Now, the actual y value that we just saw was 40, right? That's right here. The predicted y value, you could see we just came up with this right over here, was 29.24. So, if we were to work this out, our residual, and by the way, this is when x is equal to 2, would be 40 minus 29.24. Well, your residual, I can real quickly, with the calculator or without, tell you that that's going to be 10.76. What's that really saying? When your residual is positive, it means that your actual value is going to be larger than your predicted value. So where we're going with this is actually we're going to make what's called a residual plot. A residual plot is going to look like this. We could say that we're going to look at 2, 10.76. We're going to plot the x value of 2 and this residual value. Now, 10.76, well, my goodness, maybe we could say here's 10, here's 20. And I guess what I'm really trying to get at is this. We could say at 2, we're going to go up to 10.76. It would look something like that. So what does a residual plot show us? Well, it's showing us that the actual minus the predicted is a positive value. It's showing us that our actual value is above the line of regression, above the line of best fit. Maybe this will help. As we said in class 2, when you're looking at this blue line, the line of best fit, the regression line, you could also call it, we could assume that this right here, the x-axis, is your line of best fit. we could assume that this point right here is an actual point. It's showing that that actual point is above the line of best fit. What am I really getting at? I'm talking about this right here. Take a look at this. I'm going to circle this in green. Look at this right here. Your actual point is above that blue line. Look at this. Your actual point is above that blue line. It's as if we took this line of best fit and we're spinning it down, we're rotating it till it goes on top of the x-axis. And this point right here is 10.76 steps above that prediction line. So that's really what we get for residuals. Residuals are a way of showing us how good our regression line fits the data. So look, you could also have, for say number 2, when we looked at say number 2 here, it said x equals 7. At x equals 7, and by the way, we can come right over here and say, well, at 7, we have an actual data point of 123. 123 pennies are needed to break 7 strands of spaghetti is what that's saying. But what about the prediction? You can plug in a 7. 7 times 21.88 minus 14.52. That's 138.64. That's 138.64. Now, the actual was 7 pieces of spaghetti is 123. So let's just go ahead and see if we could put that together in a different way. We can say, look, the actual is 123. Here's 7. And of course, we're going to get a predicted amount, aren't we? That's 138.64. So, if I may, this point right here is 7, 138.64. This is your predicted point, or your predicted value of 138.64. Well, what are we seeing? You've got your actual point. I'm going to, maybe make that in green right here. And we could try to find our residual. Let's do that real quickly. If we just did a residual for x equals 7, it's going to be the actual minus the predicted. And you could see that we had the actual was 123. The predicted was 138.64. So what is our residual going to equal? Well, our residual, guys, is going to be something negative, isn't it? It's going to be negative 15.64. Negative 15.64. What are we seeing? When our residual is negative, it means that our actual value is actually going to be smaller than our predicted value. That's what it's really saying. So our residual plot is going to be 7 comma negative 15.64. So if I may, like here's a 1, 2, we could say 3, 4, 5, 6, 7 right over here. Here's negative 10, here's negative 20. 7 comma negative 15.64 would be right over here, wouldn't it? What are we getting at? Well, again, this would be like where our actual point is in relation to the line of best fit. you could see that our actual points below. And look, if I put a circle around that, we came back right over here, that's what that circle is showing. The actual point is 15.64 steps below the predicted line, the line of best fit. So I hope this is helping. That's how residual plots are made, and that's really what they communicate.